Hi friends, in this video we're gonna see RISC type of design architecture of a processor CPU. Okay, so in the previous video we have seen RISC type of design architecture. Now in this video we're gonna look after RISC type of architecture. The first feature of RISC is it is power efficient. Okay, it consumes less power than compared to CISC. And the next feature is pipelining. Okay, we know that pipelining is the alignment of instructions in an order for easy access of the instructions. Okay, so this is the important feature of RISC which is not found in CISC. Okay, the next is reduces instruction cycle at cost of instruction per program. This is just opposite to CISC, right? In the CISC, what we did is we reduce the instructions per program at the cost of instruction cycle. But here we reduce the instruction cycle at the cost of instructions per program, which is more efficient than, or which consumes less time than compared to CISC type of processors. Okay, as instruction cycle is less, although there might be many instructions, okay, which are to be executed, it consumes less cycle of time for that, so we get the output in very few seconds or very microseconds. That means we say it as in one cycle approximately. And the next is high performance over CISC. We already seen how we calculate the CPU performance. It is seconds per program, that we divide it into instruction cycle and instruction count and clock cycle. Based on that, if you compare with the CISC, it has higher performance than that. Next is simple instruction and executes within a cycle. There we took the complex instruction. That's why we got the name as complex instruction set computer. Here it uses only simple instructions. That means neither of the instructions are embedded under the main instruction. Here we use just the instructions directly and we execute within a cycle. As they are simple instructions, they take smaller time, or they consume less time than compared to the complex instructions. Okay. The next is RISC architecture. Here we provide hardware control unit, data path, and we have data cache and also instruction cache, and both are given to the main memory. These are the RISC architecture. This is the RISC architecture. Next is main characteristics of RISC. First thing is simple instructions usage. Right? We use simple instructions. There we used complex instructions for execution of the program. Next is supports simple data types. It supports few data types, but it supports simple data types. Okay. Then simple addressing modes and fixed length instructions for pipelining. Here, simple addressing modes. There we use complex addressing modes, or they use different types of addressing modes. Here we use simple addressing modes, then complex addressing modes, and fixed length instructions. There we used variable instruction lengths. Okay, depending upon the consumer, depending on the programmer, we change the length of the instructions. But here it is fixed length. That means if it is 2 bytes, then it is 2 bytes. If it is 4 bytes, it is 4 bytes. It does not vary according to the programmer. Okay, because of the feature called pipelining. We use fixed length here for pipelining because in this process there is no call operation like call and return. We have call and return for every processor, for every programmer. Okay, but here we don't find that call and return. Okay. Next is, for that reason we usually fixed length instructions. Okay, because the parameter can't be passed at the time of calling. Directly we use a fixed length and we cannot change it further. And it permits use of register. And remember one thing, CISC is software type of processor, RISC is hardware type of processor. Here there will be more number of registers than compared to the microprogramming instructions. There were microprogramming instructions. That means software is more, and that means instructions are more. Okay, here instructions are less, although instructions are more. If instructions are more, even though we have more registers here than compared to microprogram instructions. And execution time is 1 cycle. The approximated execution time for every program is 1 cycle. Then instruction time is same for all the instructions under the pipelining. Okay, the instructions which are under the pipelining take same interval of time for execution. The next is more RAM is needed to store assembly level instructions. Okay, and use of less number of transistors here. Okay, as we are using data registers. Okay, and no need of more memory or no more addressing modes are not required, and more instruction formats are not required here. So we use only less number of transistors than compared to RISC type of processors. And here less number of instructions are addressing modes. We use less number of instructions than compared to RISC. That is microprogrammed, so we need to use more number of instructions and more number of addressing modes. Whereas here it is using directly registers, and the operations will be between two registers, not with memory and registers. So there is only need of few type of instructions and few type of addressing modes here than compared to RISC type of processors. Okay. Now this RISC type of processors lead to an important feature or a new feature called overlap register windows. Okay. Now if you see any high level programming languages or high level programming, okay, there we use terms called call and return the procedures, right? Okay, and here when we translate that high level programming to machine level programming, okay, when we translate this to machine level programming, this call operation or call programming gives us the basic instructions which will affect the parameters of the procedure. Okay, that means it provides us the instructions which are required to pass the parameters and that are needed to call the subroutine and to execute the body of the procedure. Okay, in the same way, if we call the procedure return after the procedure is completed, and if we call the return, then the return gives us the restores the original values of the register. Okay, and it passes the result to executing calling program. Okay, and return the subroutine, return from the subroutine. Okay, these are the features which we obtain after once we translate the programming language to the machine level language. Okay, but here in this RISC type of processors, that call will be allocating, okay, the call and return. As I already mentioned, we cannot execute call and return here in this processor. That call will execute a separate window of some registers here, and every time we call the program or every time we initiate the call, then separate window will be created by the call instruction. Okay, here you can see that I have 4 different types of windows. This is my window A, window B, window C, window D. Okay, every window has some registers. Okay, before going there, these registers or these windows are created using the pointers. Okay, whenever we create a pointer, that means whenever we call the instruction, we call the procedure, then a pointer is created and that pointer is referred to a new window. If we increment the pointer, that creates another window, another register window. Okay, and if we decrement the pointer, then what happens is it deallocates the window and it points to the previous register window. Okay, now if you see here, this is a system example. For example, this system which has total 74 registers. Okay, out of which I have 10 registers which are global registers. Okay, 10 registers which are global registers, which are storing the parameters which are required for all the procedures. And here I have given names for individual procedures. These are the 4 types of procedures here. Okay, procedure A, procedure B, procedure C, procedure D. Now these global registers from 0 to 9 are used to hold the parameters which are required or which are used in these 4 procedures commonly. Okay, next is I have in each window I have 10 normal registers and 6 sharing registers. 6 sharing registers and 10 normal registers. We'll see what are those. First is here 6 registers, okay, into 4. Okay, in each window we have 2 into 6 registers and 1 into 10 local registers. Okay, here 16 to 25 are local registers to A. These local registers store local variables of the procedure. Of that procedure, they store the local variables of that procedure. Next is common registers. Common registers are 6 between each and every procedure. Suppose here are common registers between A and D. Here are common registers between B and C. Here are common registers between A and B. Okay, these are 6 registers which are responsible for sharing the parameters from each procedure to another procedure, like procedure A to procedure B. Okay, then whenever I am calling procedure A to procedure B, these are the registers which are sharing the parameters between the procedure A and procedure B. Okay, they are responsible for exchange of parameters. Okay, here in register windows, what overlap register windows, what is the main theme is we can share or we can exchange the parameters without actually moving the data. Okay, like now I suppose, consider an example, I call the procedure A and call the procedure A with to procedure B. Okay, now what happens is these are the registers which are storing my which are commonly storing my or exchanging my parameters between A and B, and these are the registers which are required locally to hold my local variables. Okay, these are the global variables holding registers, right? So this is how this overlap register window plays a major role in RISC processors. RISC processors use this type of concept, this type of feature in their programming. Okay, so once again, these are the set of instructions, or these are the set of registers here we use for 74 registers. Okay, and each window will be having 10 local registers and 6 sharing registers. Okay, and 10 are global registers. So 6 sharing registers plus 10 local registers equal to 16 for each window. 16 into 4 windows about 64, and 10 global registers, totally 74 registers according to the given R0 to R73 registers. Okay, now here what we'll do is we'll see what is the window size, window size required, and what is the register file total register size. Okay, for that a simple assumptions we do is I'll say let the global registers be denoted by G, okay, and local registers be denoted by L. Local registers be denoted by L, and common registers be denoted by C, and window size be W. Okay, our number of windows, you say it is number of windows, not window size. It is number of windows is W. Okay, so for knowing the window size, or for knowing the window size, it is L plus 2C plus G. Okay, now we'll calculate for this example here. What are my local registers? How many are there? They are 10 plus 2 into how many registers I am sharing commonly between two procedures? They are 6. How many global registers I have? 10. That is total is 32 registers. That means my window size is 32 registers. Similarly, if I want to know how many registers totally required in entire procedure or for every processor, that means total number of registers required for the processor. Total number of registers required for a processor are given by L plus C into W plus G. Okay, L plus C W plus G registers. Now if we calculate this will be 10 plus 6. What I said? This is number of windows. How many windows I have? 4. Right? 4 plus global registers are 10. This gives me 16, 4 are 64 plus 10, total of 74 registers. So overall, in my processor of RISC type, I have 74 registers in the system. Okay. Now this is the concept called overlap register windows and their usage. And this is all about RISC type of architecture design of CPU. That's all for this video. Thank you.